Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 2. Today we are continuing on with our discussion in regards with energy. Um, Last time our discussion was focused on spontaneous reactions. This time it's a little bit related. It's called entropy, which is a measurement of randomness of molecules. So today I hope everyone will realize how spontaneous reactions is related to entropy, as well as how you can actually measure entropy. So the goals of today's lesson includes for us to be able to predict the spontaneity of a process based on entropy. We've discussed this a little bit when we were talking about the spontaneity of a process, and you can identify the spontaneity of a process if you can identify the enthalpy and entropy. More importantly, if you can identify the entropy of the reaction. Also, for us to be able to explain what second law of the thermodynamics is and its significance, and a little bit also about the third law of thermodynamics. And lastly, for you guys to be able to calculate the equilibrium constants and the pressure of concentration in reactants or products in an equilibrium mixture. So let's begin our discussion with entropy. So basically, entropy, like I've already mentioned, is a measure of molecular randomness. It's basically the random movement of the molecule is entropy, no? For example, solid with a rigid structure has very low entropy. This is because solid stays on its own. No, it's a very organized structure. It's very rigid. The particles included in solid does not travel, far distances. It stays within the sphere of its solidity, and that and because the position of those molecules is very rigid, it has a very low entropy. And gases, as opposed to solid, has very high entropy. This is because the molecules of gases are in constant random motion. We've discussed this when we're talking about phases of particles. No, when we are talking about phases of matter, we know solid, liquid, and gases, and we've discussed how particles in gases behave. They are in a constant random motion. Hence, because they're in a constant random motion, that which is a measure of molecular randomness, the entropy means in gases state of solids or of gases state of matter has very high entropy. As example here, no? So you can see if you condense everything and create a one singular orb with all of those particles inside the orb, the entropy of that orb, making it solid, has very low entropy. But once all of those particles exploded into a more random motion, it has a very high entropy because the randomness of the motion of those particles. And this is related with the second law of thermodynamics in a way that the second law of thermodynamics states that as energy is transferred or transformed, more and more of it is wasted. So for example, if you have heat energy that you want to use for mechanical energy, for example, you want to use the combustion heat from burning fuel, into mechanical energy that could put your car in movement, no? As you burn that gasoline, it has a tendency, the particles within that gasoline has a tendency to degenerate into a more disordered state. So we've discussed this a little bit from our previous discussion, wherein the world has a tendency to direct itself into a more disordered state. And we've discussed this in a way, yung burger na kinain natin, and also in burning paper. The particles of the paper at the beginning are very solid. Paper is a type of solid matter, no? The particles within that paper are in a rigid structure, but when you start burning it in a process which is a very spontaneous process, the particles of solid start to scatter. Some of them, becoming ashes and sticks on the ground, and some, starts to fly in the air. Some of them even become gas particles, no? And the gas particles start to spread everywhere. And that's why we mentioned that release of energy or release of heat is a very spontaneous process because there is an increase in entropy, there is an increase in the randomness of those particles, making it an spontaneous reaction. Moreover, entropy is also a measure of system's thermal energy that is unable to do useful work. And if we go back to the example of a burning paper, at the start, the burning paper has releases energy in a form of heat, no? And that heat you can actually use it as a to do as a form of to do work. Example, gasoline. When you start burning gasoline, the heat and the combustion that comes from burning gasoline can be used in order to move your car. Now we can use that thermal energy to do work, which is thrusting your car or making your car be able to move or to be able to travel. But over time, as we keep burning that gases, the particles in the gases, no, as they oxidize and as they release dun sa tambutso ng car mo, yung particles na nanggaling dun sa petroleum mo, dun sa gasoline mo, is unable to do work once na na-release na siya sa tambutso, no? Because hindi mo na siya mababurn. So that thermal energy that resulted from the end product of burning that gasoline is not able to do work as well. So that's why we can also think of entropy as the systems yung the in a way that the randomness of the molecular structure cannot able to do work as well. And lastly, entropy, like enthalpy, is a state function. We are only focusing on the initial and the final state. So we are only focusing, for example, dun sa initial state ng paper and dun sa final state ng paper. Initial state niya is solid and the final state niya, we can think of it as, gas. No? We do not care on how it arrived from its initial to final state. We are only focusing on the state of yung state niya, yung phase state niya. Is it solid or is it gas in its final state? We do not care on how it arrived there. That's why we call them as a state function. Therefore, we can actually solve entropy, or more specifically, the change in entropy by using this equation. The change in entropy of a system is basically taking the entropy in its final form, subtracted or minus the entropy in its initial form or its initial state. So we will go back to this equation later on as we solve for entropy. But just remember this, since entropy is a state function, meaning again, we're only focusing on the state of the system in its initial and final status. So in its initial status, like a burning paper, it is paper. After burning it, we are focusing in the particles of that burnt paper. You can think of it as ashes in the air or basically gases, no? And in order to measure how much change in entropy yung nangyari, we can take the entropy of its final state and minus the entropy in its initial state. So when this change in entropy is positive, the reaction is spontaneous. If this becomes negative, the reaction is non-spontaneous. So what are some of the factors that can influence entropy? We are going to focus two things that influences entropy of the system. One is temperature and the other is the number of particles. Temperature, because when we increase the temperature, it can result in a change of entropy in a way that it increases the kinetic energy. If you guys remember, we've talked a lot about this, no? Babalik-balik tayo halos. That when we have more thermal energy, it means there is more heat in the system. There is an increase in the kinetic energy of the particles, and when there's increase in the kinetic energy of the particles, they are moving much faster. As opposed to there is less temperature, there is lower temperature, the movement of the particles is much slower because the kinetic energy is much lower. Therefore, if we can actually lower the temperature indefinitely, we can arrive at a point wherein the entropy becomes zero. The entropy becomes zero when the temperature is actually at 0 Kelvin. So in this state, This is actually how the third law of thermodynamics state that when we have a 0 Kelvin temperature, the entropy is zero. So by lowering the temperature, we can arrive at a condition wherein we have zero entropy. And yeah, so temperature can influence the entropy of a system. Increasing the temperature increases the randomness of the movement, therefore there is an increase in entropy. Lowering the temperature will eventually result in a condition that has zero entropy. Also, the number of particles in a reaction or in a system affects the entropy. Reactions that produces much higher number of products particles than the reactants are examples of a spontaneous reaction then, and this leads to the increase in entropy. How can we have a higher product than the reactants? No, when we are talking about moles. So, for example, in this situation, we have 1 mole of CaCO3 CO3 here, no? And in this decomposition process, we're in Ca and CaCO3, calcium um, carbon trioxide. I'm not sure. I've carbonate. So calcium carbonate. So this is calcium carbonate decomposes into calcium oxide and CO2, carbon dioxide. What you can see here is we have 1 mole of. So let's use the pen here. We have 1 mole, basically 1 mole of CaCO3, calcium carbonate, and then we have 1 mole of calcium oxide and 1 mole of carbon dioxide. So if you guys remember in the chemical equation, the coefficient of these are basically 1. And as you can see, basically in this situation, in your reactants, you have 1 mole, total of 1 mole of the product or the reactants. But for your product, what you can see is you have you have 2 moles of product. So there is a higher number of product particle. You have higher number of molecular particles in your product um, than when they are in reactants. So when you have this type of situation where you have higher moles of product than the reactant, the process usually is a spontaneous process, and it increases the entropy. It increases you have a positive entropy. It increases the disorder in the universe. No? And this is also part of the second law of thermodynamics. But if you have a situation wherein the reactants are fewer, the reaction has few products than they have in the reactant, there is a negative entropy and therefore it is non-spontaneous. As for example here, no, you have 1 mole. So you have 1 mole of dinitrogen and you have 3 moles of dihydrogen. So for your reactants, you basically have 4 moles of reactant. But your products, you have 2 moles of product. So you have higher reactants than when you have higher number of molecular particles in your product. In this type of situation where you have higher reactants or higher number of particles in your reactants than in your products, these type of reactions are usually non-spontaneous. And remember, non-spontaneous reactions usually have negative entropy because it does not increase the disorder in the universe. It does not increase the randomness of the particles, but it favors the reactants. Okay, so these two are very important. I want you guys to remember them, no, and how they increase or how they influence the entropy of a reaction. Now let's continue on. So let's look at these examples right here. Wherein you started with a solid and then you are increasing the temperature in that solid. So for example, let's take ice, no? So ice begins with solid. So ice, since it is a solid structure, can have a zero entropy. No, it's not disorganized. The structure of the particles in ice are solid in a rigid structure, therefore it has a very low entropy. At this point, let's think of it as having zero entropy. But as we increase that temperature, the particles in the solid starts to vibrate, no? They vibrate and they vibrate and they keep vibrating as you increase the temperature until such a time that it reaches the melting point. So what happens to the ice? It changes its phase from solid to liquid. And what happens is when that point reaches, there's actually a sudden increase in the entropy. This is because we have more particles uh, that changes its motion. So instead of vibrating alone, kasi yung solid, no, let's think of this as our ice cube. So yung particles mo dito, nagva-vibrate lang sila. Pero when you have a solid, the particles are more freer to move, no? Unlike the solid, wherein they only vibrate in their position, for liquid, they have more positions to go to. Of course, hindi sila nagtatravel na malayo. Depende siya sa shape ng water, this container. But yung movement ng mga particles sa liquid are much freer than water. Therefore, when it reaches higher melting point, there's a sudden increase in the entropy. So that's positive change in entropy, making it a melting as a spontaneous reaction. No? And we discussed this. We've discussed that melting ice is a spontaneous reaction. But if we keep increasing the temperature, the liquid here it starts to move faster and faster. The particles it starts to move faster and faster, no? And to the point that it starts to boil. Your water starts to boil. So there is a change in phase wherein the particles changes from liquid to gas. And for gases, we've discussed earlier, they are more freer, they are more spread. No, they're basically everywhere. There is a constant random motion, and there is a massive increase, or there's a massive jump in the entropy, especially as we increase the temperature. These particles right here has a very high kinetic energy, so they're moving very fast, and as we keep increasing that, they'll keep increasing the entropy because they'll move faster and faster, and they move basically everywhere. The randomness of their motion is increasing. So this is how temperature affects entropy, no? And the same way how the particles relate to the randomness of their motion in regards to their phases as matters. So particles in liquid state are more random than when they are in solid state because they can have vibrational, translational, and rotational motions. So these types of electron or particle motion, no? Particle motion. So vibrational usually is only in solid because they stay in their position, they do not rotate, but they just vibrate in their position. But once you start to have liquid and gases, the particles starts to not only vibrate, yeah, they still vibrating now, even though they're liquid and gases, they're still vibrating in their position. But moreover, they are also traveling, no translational. You guys remember in physics, translational a translation, we've discussed that. It's basically a movement along an axis, like a straight line. You can have x-axis, you can have which is our y-axis. But basically, in liquid form, the particles can travel in a translational, so they can travel here, they can travel there, they can travel in one axis. But also, the particles here, they can rotate on their own, which cannot happen in solid. The solid states, they do not rotate, but they just vibrate. But when they are in solid and liquid gases, they can have they can also rotate in their axis, no? So for example, you have this particle right here. Now it can rotate on its own, either that way or this way. Not only that, they can also travel. This is a translational travel, and they can also vibrate. And all of these different ways of the particles moving affects entropy. That's why there is a sudden increase in entropy, because not only can these particles vibrate, they can also travel translationally, and they can even rotate, and that increases affects entropy. Moreover, when it is in gas, no, kasi when it's in gas, not only is this happening, but translational is more expanded. Gas can travel more wide for distances. It can, it can move to much bigger space. Of course, that depends on the container, but if it is an open space, it basically travels everywhere. So that increases the randomness of the motion. Therefore, you have a massive spike in the entropy. So I hope that's clear on how temperature and how the movement affects the entropy of a substance or a reaction. So, and also particles in gaseous phase are more random than liquid, therefore it has higher entropy. Yeah, no? So you have crystal in solid, liquid, and gases, the entropy is increasing. There is a positive entropy, and it's usually a spontaneous reaction when you are melting. But when you want to freeze something, when you want to condense gas to liquid and freeze gas to solid, it is a non-spontaneous reaction because there is a negative entropy happening. You are making the particles more structure, you are making it less random in their motion. So in the end, we can measure entropy, no? And one way that we can measure entropy is using what we call the standard molar entropy, which is we write here delta, and then there's a degree or S, and then we just write the degree that denotes a standard molar entropy. But what is a standard molar entropy, no? Standard molar entropy is basically the entropy of 1 mole of a substance under a standard condition. The reason that we have to do this, we have a standard condition, 1 atmosphere to 25 degrees Celsius. It's simply because as we increase this temperature, um, there is an increase in entropy. So by having a standard temperature and a standard pressure, we can create a standard wherein we can measure the entropy of a given substance. So we call that the standard molar entropy. So we take 1 molar concentration of a substance and subject it into 1 atmospheric pressure under 25 degrees Celsius, and then measure the entropy or measure the randomness of the motion of the particles of that substance. And these values are usually tabulated, so you don't have to measure this. These are all, the particles are already measured for you. What you want to solve then is the change in standard molar entropy. So that's what we're going to do. We are going to measure the change in the standard molar entropy. So how can we do this? So we're going to go back to the first equation that we've discussed earlier. We know that we can measure the change in entropy by taking the entropy of the final state and the entropy of the initial state, basically subtracting the entropy of the initial state from the final, and then we can change or we can measure for the change in entropy. We can apply this in solving for standard molar entropy. Now, so we can have the standard molar entropy of your products, which is your final state of your reaction, and you minus the um, sum of all the standard molar entropy of your reactants. Reactants being your initial state of your reaction, and then the end products are the final state of the reaction. The sum, because sometimes you have 2 or more products or 2 or more reactants. No? That's why we have to take the sum of their standard molar entropy. Again, the standard molar entropy are given. So by doing this, taking the sum of all the standard molar entropy of your products and minus the sum of all the standard molar entropy of the reactants, we can solve for the change in the standard molar entropy of the reaction. So in general, if you have this equation where A plus B, A capitals A and B are your reactants, and small letters A and B are their coefficient, or basically their molar concentration in the reaction, and they changes to, or they move to products C and D. So C and D are your product molecules, and capital C and D, small letters C and D are the coefficient, or basically the molar concentration of the products. You can measure the change in standard entropy using this equation. Wherein basically the standard entropy of your C plus the standard entropy of your D, since C and D are your products, and you have to take their standard molar entropy and multiply it by however how much molar it is they exist in the reaction. No? C multiplied by the standard and molar entropy of your C plus D multiplied by the standard molar entropy of D, and this is your the sum of all your products minus the coefficient, or however how much molar concentration of reactant A you have. So multiply the coefficient of A to its standard molar entropy plus the coefficient of B multiplied by the standard entropy of your reactant B. So doing this equation, you can solve for the change in the molar standard molar entropy. So let's have the sample problem to show you how we can solve for the change in the molar standard entropy. So consider the composition of calcium carbonate, the mineral found in limestone. Given the balanced chemical equation and the data from the table below, calculate the change in the molar standard entropy. So we have our substances here, and they gave us the standard molar entropy, meaning this is the entropy of this substance when you have 1 molar of that substance and 1 molar of that substance under 1 atmosphere and 25 degrees Celsius. So this is basically your given na, no? So if we're not gonna write the given anymore, so you have the standard molar entropy of calcium carbonate, which is 92.9, calcium oxide 39.8, and carbon dioxide, which is 13.6. And also the molar concentrations of your calcium carbonate is basically 1, and all their molar concentrations as reactants and products is basically 1. So that's we're not going to write the given anymore, but basically what it's asking is what is the change in the standard molar entropy, and the equation that we have to use, or the formula that we have to use, is basically the long equation that I showed earlier, but I'm just gonna write the shorter one, which is the sum of all the standard entropy of your react or your products minus the sum of all the standard entropy of your reactants. No? So let's have solution. So in order to solve this, what we're going to do is take the change in the standard molar entropy is equals to the sum of all the standard molar entropy of the product. Our product is calcium oxide and carbon dioxide. So we will have S and CaO, CaO plus the standard molar entropy of CO2 minus the standard molar entropy of your reactant, which in this case is calcium carbonate, CaCO3. So that would give us, so the standard molar entropy of CaO, calcium oxide, is 39.8. So that's 39.8. This is the unit for standard molar entropy, which is joules per molar Kelvin. We usually use Kelvin for our temperature, and the temperature that is under it, that is standard, is actually 239 Kelvin. I believe that's equal to 25 degrees Celsius. So the molar standard entropy of CO2 is 213.6 joule molar Kelvin minus the standard molar entropy of your reactant, which is calcium carbonate, is 92.9 joules per molar Kelvin. So just plug that in your what do you call this, on your calculator. You would get, so 39.8 plus 213.6, and then after you add this, you minus it to 92.9, and that would give you 160.50 uh, joules per molar Kelvin, or joules per molar Kelvin. Okay, as you can see, we have positive entropy. So remember, positive entropy is a spontaneous reaction. And look at discussion kanina, no? We know that this is the example that we have earlier, that we know that this should be a spontaneous reaction kasi our reactant has 1 mole, pero our product has 2 moles. So there is an increase in the number of particles in our product, making it a spontaneous reaction. And remember, spontaneous reaction should have a positive entropy. And as you can see on our answer, we have a positive entropy. So it checks out, no? So having a positive entropy, change in standard molar entropy, we know that this equation right here is spontaneous, no? So I hope you guys remember this. Remember, if you have a higher product than reactant during the equation, or during the reaction, then this is a spontaneous. And from our previous discussion, spontaneous reactions have positive entropy. And as you can see, our entropy is measured to be positive. So that's how we can solve for the change in the standard and molar entropy of the reaction. Okay, so I hope that's clear, but let's take sample number 2. Consider the Haber process for the industrial synthesis of ammonia involving gaseous species. So this is how we actually make ammonia industrially, no? Mass-produced ammonia. Given the balanced chemical equation and the data from the table below, calculate the change in the standard molar entropy. So we have nitrogen, dinitrogen, 1 molar dinitrogen, and 3 molars of dihydrogen, and then it can create 2 moles of ammonia, which is NH3. No? So this is basically our given. And as you can see, we have 1 mole of N2, we have 3 moles of H2, and we have 2 moles of our product. And as you can see in our reactant, we have 4 moles of our reactant, but we only have 2 moles of our product. This already tells us that this is non-spontaneous reaction. You guys remember that? We have lower product than number of particles in our reactants. And remember that non-spontaneous reactions have what? Negative. They have negative entropy. So expect that the entropy for this substance, for this computation, should be negative. So let's head to the solution. No? So I'm not gonna write the ask anymore and the formula. It's the same ask and formula from the previous problem. So we're gonna go straight on to the solution. Okay, so as for solution, we have delta S. It's change in the standard molar entropy. You have um, you know you only have one product, so we begin with the product, which is the standard molar entropy of your product, which in this case you have NH3, but you have 2 moles. Okay, so let's write that as, so this is the coefficient. Remember, you have the coefficient, and then the S of NH3 is NH3. So that's the product minus the reactant. So as for reactant, we have only 1 mole of N2, so that's only the um, S, or the standard molar entropy of N2 plus, you have 3 moles of H2, so that's 3SH2. So just substituting the number, you have 2 multiplied by NH3, that's 192.3 joules per molar Kelvin, minus the standard molar entropy for N2, which is 191.5 joules per molar Kelvin, plus you have 3 multiplied by, so 3 because they have a coefficient of H2 is 3, we have 3 moles of H2, and the standard molar entropy of H2 is 130.6 joules per molar Kelvin, per mole Kelvin. So just plugging in those numbers, we would get um, equation, just so 2 times 192.3 and then minus 191 plus 3 multiplied by 130.6. You would get negative 198.70 joules per molar Kelvin. And as you can see, like I've mentioned earlier, we should have negative entropy, and it checks out. No, this is because we have more particles in our reactants than when we have in our products, making it a non-spontaneous. And non-spontaneous we know has negative entropy, and we have negative entropy. Therefore, this equation right here is a non-spontaneous reaction. Okay, so that's how we measure entropy, and that's how we can identify whether the reaction is spontaneous or non-spontaneous using entropy. I hope it's clear. If you guys are confused or have any question, do not hesitate to message me. Thank you so much and have a great day.